Dear students, after studying this module, you shall be able to learn about the basics of supramolecular chemistry, know about non-covalent interactions, understand the concept of self-assembly and self-organization, and also learn and analyze host-guest chemistry. Students, in this module, we shall be learning about various aspects of supramolecular chemistry. So, one question arises in mind is that what is the basic definition of supramolecular chemistry? So, supramolecular chemistry is a highly interdisciplinary field of science covering the chemical, physical and biological features of the organized chemical species of greater complexity than molecules themselves, and these are held together and organized by means of intermolecular, that is non-covalent binding interactions. In other terms, you can put it like this can also be defined as a chemistry of molecular assemblies and of intermolecular bonds. Professor Jean-Marie Lehn won the Nobel Prize in 1987 for his contribution and work in the area of supramolecular chemistry. Basically, supramolecular chemistry was defined in terms of the non-covalent interactions between a host and a guest molecule. The non-covalent interactions such as electrostatic interactions, hydrogen bonding interactions, van der Waals forces define the intercomponent bond between the molecular individuals and populations. These non-covalent interactions, as I have told, are as important in supramolecular chemistry as covalent interactions are very important in case of classical organic chemistry. So, you know how much importance does a covalent bond between a carbon-carbon holds in case of classical organic chemistry when we talk of classical organic compounds. So, in case of supramolecular compound students, we shall take care that these interactions, apart from the covalent ones, they play a very important and a vital role in supramolecular chemistry. The energy of these non-covalent interactions is much smaller than 200 to 400 kilojoules per mole, which is typical of a covalent chemical bond. In addition to relatively strong ion-ion electrostatic interactions of say 100 to 350 kilojoules per mole and hydrogen bonding, which is about 10 to 120 kilojoules per mole, they include much smaller forces like London dispersion forces, ion induced dipole and dipole-dipole interactions that are in the range of 5 to 50 kilojoules per mole and stronger. Supramolecular chemistry covers the crystals, solutions and also the polymers in which non-covalent interactions play a very vital and an important role. Generalizing students, supramolecular chemistry thus involves the self-assembly and host-guest systems using a variety of these interactions, as I have told you, some of which are clearly non-covalent, for example hydrogen bonds, and some of which possess a significant covalent component, for example when we talk of the metal ligand interactions in this module and in next modules which are to come. It is important to note here that supramolecular chemistry has also diversified enormously and includes charge transfer complexes, inclusion complexes which incorporate CRAMS hemisarands and cyclodextrines, mono and poly layers, micelles, vesicles, liquid crystals and co-crystals consisting of at least two different kinds of molecules which form highly specific domains differing in the objects studied and research techniques. The specificity and separateness of the charge transfer complexes and those of liquid crystals seem generally recognized. On the other hand, students, as concerns inclusion complexes or other molecular aggregates consisting of only few molecules, higher molecular aggregates and co-crystals formed by at least two types of molecules, the situation is not that clear as of now. Now, after having introduced you to the very basic aspects of supramolecular chemistry, let us now concentrate on non-covalent interactions. The supramolecular chemistry generally concerns non-covalent bonding interactions such as ion-ion interactions, ion-dipole interactions, dipole-dipole interactions, hydrogen bonding, cation-pi interactions, anion-pi interactions, pi-pi interactions, closed shell interactions, van der Waals forces and crystal close packing. So, the term non-covalent encompasses an enormous range of attractive and repulsive forces. So, just to reiterate, it encompasses both attractive as well as repulsive forces or effects which are apart from the covalent bonds. Now, you can see this figure. Here we have shown you the comparison between the scope of molecular and supramolecular chemistry according to Len, who I told you he has won the Nobel Prize for his contribution to supramolecular chemistry in 1987. The ion-ion interaction, as in ionic cube lattice of solid sodium chloride, in which each sodium cation is surrounded by 6 chloride anions. The sodium cation is able to organize 6 complementary donor atoms about itself in order to maximize the non-covalent ion-ion interactions. The ionic cubic lattice of solid sodium chloride breaks down in solution because of solvation effects to give rise to species such as the very labile and octahedral, which is the sodium hexahydrate, that is the sodium H2O6 plus cation, that is it is surrounded by 6 molecules of water. The bond strength of ionic bonding is comparable in strength to covalent bonding and bond energy is in the range of 100 to 350 kilojoules per mole. And now here we are showing you in this figure the ionic cube lattice of solid sodium chloride, and another one, this figure B here, it's showing you the supramolecular ion-ion interactions by anion and an organic cation, and the third figure is showing you the supramolecular ion dipole interactions by metal cation and crown ethers. So, you can realize how many forces come under the non-covalent interactions. The bonding of an ion such as, let us say, sodium with a polar molecule such as water, as obtained when you dissolve the salt or the NaCl crystal in water, is a classical example of ion dipole interaction, which ranges in the strength from 50 to 200 kilojoules per mole. This kind of bonding is seen both in the solid state and in the solution state. The ion dipole interactions in supramolecular structures of the complexes of alkali metal cations with macrocyclic, that is large ring ethers, they are also termed as crown ethers, and we shall be taking them in detail in the future modules. In these crown ethers, the ether oxygen atoms play the same role as the polar water molecules as when they hydrate the sodium cation. Although the complex is stabilized by the chelate effect and the effects of macrocyclic pre-organization. A hydrogen bond may be regarded as a particular kind of dipole-dipole interaction in which a hydrogen atom is attached to an electronegative atom, or say an electron withdrawing group is attracted to a neighboring dipole on an adjacent molecule or a functional group. Hydrogen bonds are commonly written as DH and there is a dotted line which is connected to A. that these are the individual atoms of molecules and usually involve a hydrogen atom attached to an electronegative atom such as oxygen or nitrogen as the donor, which is demarcated as D here, and a similarly electronegative atom often bearing a lone pair as the acceptor, which is termed as A. So now I hope you understand what is D, covalently bonded to H, and then dotted line with A, which is the acceptor. The typical range of hydrogen bond strength ranges from 10 to 120 kilojoules per mole, and the typically hydrogen bonded O.O distances are 2.50 to 2.80 angstrom in length, though interactions in excess of 3 angstrom may also be very significant if they are strong. Students, taking an example of hydrogen bonding, let us look at the next figure, in which you can see a shift in the frequency of the OH stretching, that is the infrared stretching frequency, from about 3400 centimeter inverse to as low as 2500 centimeter inverse, accompanied by a significant broadening and intensifying of the absorption bands. Hydrogen bonds are ubiquitous in supramolecular chemistry. In particular, hydrogen bonds are responsible for the overall shape of many proteins, recognition of substrate by numerous enzymes, and along with pi-pi stacking interactions for the double helix of the structure of DNA. Now in this figure, clearly it shows the supramolecular hydrogen bonding interactions in first, as I told you, the carboxylic acid dimers, which is a very good example of hydrogen bonding in case of supramolecular chemistry. And second, you will see the hydrogen bonding interactions between the organic molecule, and the C and D show you the guanine and cytosine base pairs of DNA, and how the hydrogen bond stabilizes the DNA by base pairing between these two bases. The pi-pi interactions occur between aromatic rings, so sometimes it is also called aromatic pi-pi stacking interaction. Often in situation where one is relatively electron rich and the other one is electron poor. The typical range of such pi-pi interactions is from 50 to 500 kilojoules per mole. There are two types of pi interactions. First one is the face to face and edge to face. This is the second one. Now face to face pi stacking interactions are responsible for the slippery feel of graphite and its useful lubricant properties. Similarly, pi stacking interactions between the aryl rings of nucleobase pairs also helps to stabilize DNA double helix. Second one, the edge to face interactions may be regarded as weak forms of hydrogen bonding between the slightly electron deficient hydrogen atoms of one aromatic ring and the electron rich cloud, that is a pi cloud of another ring. Strictly speaking, they should not be referred to as pi stacking, since there is no stacking of the pi electron surfaces. Edge to face interactions are responsible for the characteristic herringbone packing in the crystal structures of a range of small aromatic hydrocarbons, including benzene. Now in this figure, students, you can see how there are many supramolecular pi-pi type interactions in various molecular structures and different type of pi-pi stacking. First one, it is showing you the face to face, the second one is showing you the edge to face interactions. Cation pi interactions. Now let us discuss this topic. Transition metal cations such as iron 2+, platinum 2+, etc. are well known to form complexes with olefinic and aromatic hydrocarbons. An example is the very famous ZC salt, whose formula is platinum Cl3C2H4 whole minus and ferrocene, iron C5H5 whole twice, that is cyclopentadienyl, and then this forms the complex. The bonding in such complexes is strong and could by no means be considered non-covalent, since it is intimately linked with the partially occupied d orbitals of the metals. Even species such as silver plus, that is a silver plus cation, and C6H6, that is the benzene ring, have a significant covalent component. The interaction of alkaline and alkaline earth metals or their cations with the carbon-carbon double bond is, however, a much more non-covalent or a weak interaction, and is suggested to play an important role in many biological systems. For example, the interaction of potassium and benzene in the gas phase is approximately 80 kilojoules per mole, and this is shown to you in figure. By comparison, the association of potassium with a single water molecule is similar at 75 kilojoules per mole. The reason for this is that the potassium ion is more soluble in water than in benzene, is related to the fact that many molecules can interact with the potassium ion, whereas only a few bulkier benzene molecules can fit around it. The interaction of non-metallic cations such as RNH3+, that is the salt of the alkylamine, with double bonds may be thought to be as a form of XH pi hydrogen bond. After having seen the cation pi interaction, students, let us move down to the anion pi interactions. So, students, cation pi interactions are favorable, obviously because one is a cation and the other one is a pi system, one is electron rich, another is electron poor. However, the interaction of an anion with pi electron density seems like it should be repulsive, and indeed the affinity of the aromatic ring containing cryptand, as shown to you in the figure, for halides rapidly falls off in the order of, that means fluorine is much greater than the chlorine, then bromine, then which is approximately similar as iodide. Because of anion pi repulsions in the case of larger halides, with all except fluorine or the fluoride anion showing constant anion ring centroid distance of approximately 3.7 angstrom. However, there is a charge difference between an overall neutral aromatic ring and an anion, and therefore, in principle, the possibility does exist for an electrostatic interaction, that is an anion pi interaction. Such short anion pi interactions have been noted for organometallic calixarine derivatives, as shown to you in the figure, where the aromatic ring bears a significant positive charge. Anion pi interactions have also been implicated as controlling elements in case of self-assembly reactions of silver 1 complexes with pi acidic aromatic rings. Now, as you can see here, the cation pi interactions, first of all in molecular structures, first is benzene, second is the ZC salt, third one is a schematic representation of cation pi interactions in between potassium ion and benzene and quadruple movement of benzene. In this figure you can see the molecular structures which are involved in the anion pi interactions as I was talking. First you can see the aromatic ring containing cryptand, and second one you can see is the organometallic calixarine derivative. Van der Waals interactions arise from the polarization of an electron cloud by the proximity of an adjacent nucleus, resulting in a weak electrostatic interaction or attraction. The typical range of van der Waals interactions strength is from 0.50 to 40 kilojoules per mole. And let us talk more in detail about the van der Waals forces now. These van der Waals interactions are non-directional and hence possess only limited scope in the design of specific hosts for selective complexation of particular guests. In general, van der Waals interactions provide a general attractive interaction for most soft polarizable species with the interaction energy proportional to the surface area of contact. In supramolecular chemistry, they are most important in formation of inclusion compounds, in which small typically organic molecules are loosely incorporated within crystalline lattices or molecular cavities. For example, the inclusion compound of toluene within the molecular cavity of para-tertiary butyl phenol based macrocycle. Now you can see here the para-tertiary butyl calixarene, calix 4-arene in this figure. So this is the X-ray crystal structure shown to you here of a typical van der Waals inclusion complex, as I told you just now, and the second one in this figure shows you the hydrophobic van der Waals interaction. Let us now talk about dipole-dipole interactions. Alignment of one dipole with another can result in the significant attractive interactions from matching of either a single pair of poles on adjacent molecules or opposing alignment of one dipole with the other, that is type 2. These are shown to you in figure. With energies of these range from 5 to 50 kilojoules per mole. Organic carbonyl compounds show this behavior well in the solid state, and calculations have suggested that type 2 interactions have an energy of 20 kilojoules per mole, which is comparable to a moderately strong hydrogen bond. The boiling point of ketones such as acetone, which is 56 degrees Celsius, however, demonstrates that dipole-dipole interactions of this type are relatively weak in solution. This is obvious by the boiling point, and this is seen here in this figure considering acetone, where R groups can be CH3, and the dipole-dipole interactions are shown to you here. So after having considered all these types of interactions involved in supramolecular chemistry and having learnt about detailed structures and them involving various such interactions, let us move down to the topic, an important topic of self-assembly and self-organization. Self-assembly is the spontaneous and reversible association of molecules or ions to form discrete extended entities at either the molecular, covalent or the supramolecular non-covalent level. Within self-assembly processes, we must distinguish between molecular self-assembly and supramolecular self-assembly. Molecular self-assembly basically concerns the formation of covalent bonds as a part of special synthetic procedure. The assembly is subject to control by the reaction stereochemistry and their conformational features of the intermediates. For example, the formation of amine aldehyde condensation macrocycles. For example, urotropine is one. The formation of supramolecular self-assemblies results from the recognition directed spontaneous association of a well-defined and limited number of molecular components under the intermolecular control of the non-covalent interactions such as coordination interactions, hydrogen bonds and dipolar interactions that hold them together. The reversibility of supramolecular self-assembly is the key to resulting systems' ability to shift through the available components to form the thermodynamically most favorable structure. Putting it in other words, students, supramolecular self-assembly concerns the spontaneous association of either a few or many components resulting in the generation of either discrete oligomolecular supramolecules or of extended polymolecular assemblies such as the molecular layers, films, membranes, etc. The term tecton has been proposed for designating the components that undergo self-assembly. Now students, in this figure you can see the Schiff-based condensation and the reduction of the product to give an amine macrocycle synthesized by aldol condensation of acetone and this nickel complex. Self-organization. Now what is the definition of self-organization? Self-organization could be considered as a set intersecting self-assembly, ordered self-assembly that would 1. Contain the systems presenting a spontaneous emergence of order in either space or time or both. Second, it would cover spatial, structural and temporal dynamic order of both equilibrium structures and of non-equilibrium dissipative structures, incorporating non-linear chemical processes, energy flow and arrow of time. Thirdly, it will concern only the non-covalent supramolecular level. Fourth, be multi-component and result in the formation of polymolecular assemblies presenting supramolecular organization and long range order, that is with or without regularity and periodicity by virtue of specific interactions operating either through recognition events between the molecular parts or in a dynamic process. The higher energy of confinement of order, that is 1D, 2D, 3D, 4D of self-assembled entities, the more they may be considered as organized molecular layers, membranes, micelles, colloids, liquid crystals, molecular crystals, entities. Self-organization thus involves interaction between parts and integration of the interactions leading to collective behavior such as found in the phase change or in the generation of spatial or temporal waves. The phenomenological description of macroscopic features of a self-organizing system must eventually find an etiological explanation at the microscopic, molecular and supramolecular levels. Self-assembly and self-organization of both supramolecular architecture are both multi-step processes implying information and instructed components of one or several types. And these may be distinguished from templating, that is mere templating. Templating is a synthetically most efficient procedure involving the use of temporary or permanent helper species of organic or inorganic nature for stepwise assembly of molecular or supramolecular structures of high complexity. Self-assembly and self-organization require molecular components containing two or more interaction sites and thus capable of establishing multiple interactions or connections. Self-complementary components associate with themselves undergoing homoassembly, where complementary components such as pleromers associate with one another giving heteroassembly. Students, the next topic under the umbrella term of supramolecular chemistry is the host-guest compounds. In host-guest compounds, generally we consider a molecule, which is a host, binding to another molecule considered to be the guest, to produce a host-guest complex or a supramolecule. Commonly, the host is a large molecule or an aggregate such as an enzyme or synthetic cyclic compound possessing a sizable central hole or cavity. The guest may be a monoatomic cation, a simple inorganic anion, and an ion pair or a more sophisticated molecule such as a hormone, pheromone or neurotransmitter. More formally, the host is defined as a molecular entity possessing convergent binding sites. For example, Lewis basic donor atoms, hydrogen bond donors, etc. The guest possesses divergent binding sites. For example, a spherical Lewis acidic metal cation or a hydrogen bond acceptor halide anion. In turn, a binding site is defined as a region of the host or a guest capable of taking part in a non-covalent interaction. The host-guest relationship has been defined by Donald Crampton, and he also received the Nobel Prize with Professor Jean-Marie Lehn and Professor J. Pedersen for their influential and contribution work in the area of supramolecular chemistry. The supramolecular host-guest chemistry generally shows the stability of a host-guest complex in solution. The chemistry of clathrates, as shown to you in the figures, and more generally inclusion, relates to hosts that are often stable only in the solid crystalline states and dissociate on dissolution in a solvent. Gas hydrates, urea clathrates, and a wide variety of crystalline solvates fall into this category. On the other hand, students, if you see the next figure, that is molecular hosts for ions such as crown ethers, cryptands and spherands, or hosts for neutral molecules such as carcerands and cryptophanes, they display significant binding both in solid state and in solution. Now here you can see in this figure, which I talked to you about earlier, which is the inclusion of guest molecules in cavities formed between the host molecules in the lattice, resulting in conversion of a clathrand into a clathrate. Second is the supramolecular host guest molecules for ions, and thirdly you can see the supramolecular hosts for neutral molecules. Now students, after having studied broadly what is supramolecular chemistry, what are basic interactions of supramolecular chemistry, and what sort of compounds can be given rise by self-organization and self-assembly, and what are the other types of host-guest compounds, now I would like to summarize this module. In this module, you have learned that supramolecular chemistry deals with the organized chemical species of greater complexity than molecules themselves, which are held together and organized by the means of intermolecular, that is non-covalent binding interactions. The supramolecular chemistry generally concerns non-covalent binding interactions such as ion-ion interactions, ion-dipole interactions, dipole-dipole interactions, hydrogen bonding, cation-pi, anion-pi interactions, pi-pi interactions, closed shell interactions, van der Waals forces and crystal close packings. In general, supramolecular chemistry involves the self-assembly and the host-guest systems using a variety of interactions, some of which are clearly non-covalent, for example the hydrogen bonds, and some of which possess a significant covalent component, for example metal ligand interactions. Self-assembling systems do not involve hosts and guests, but rather self-complementary molecules or complementary partners such as tectons, which literally means builder of self-assembled molecules. In host-guest compounds, a host component with convergent binding sites and a guest component with divergent binding sites are involved. Host molecules which are generally involved in supramolecular chemistry, such as the crown ethers, cryptands and spherands for ions, and hosts for neutral molecules such as carcerands and cryptophanes, display significant binding both in solid and solution state. So I hope students, this is the beginning of many modules concerning supramolecular chemistry. And with this modest beginning, I hope you really found this module very informative, and we shall build on this particular information and this particular knowledge of supramolecular chemistry in order to let you gain more information about the same.